What if I told you there are planets where it rains glass and temperatures reach unimaginable levels? Welcome to some of the scariest places in the universe, where worlds like Proxima Centauri b and TRAPPIST-1e challenge our understanding of life and survival. From the dark depths of TRES-2b, which absorbs nearly all light, to the stormy atmosphere of HD 189733b, let's take a journey to the most terrifying planets in the universe. The universe is vast, mysterious, and filled with wonders that defy the imagination. Beyond our solar system lies a multitude of exoplanets, planets orbiting stars other than our Sun, each offering an unparalleled glimpse into the extremes of cosmic diversity. Among these worlds are some of the most hostile and terrifying places ever discovered, where conditions challenge not only our understanding of planetary science but also the limits of our imagination. These are planets that rain glass sideways in supersonic winds, endure temperatures so high that metals vaporize, or exist in perpetual darkness due to the nature of their orbits. They are as fascinating as they are formidable, forcing us to rethink the boundaries of habitability and the resilience of life. The discovery of hostile exoplanets has been made possible through advancements in technology, including space telescopes like Kepler, Hubble, and the more recent James Webb Space Telescope, 2021. These tools have allowed astronomers to identify over 5,500 confirmed exoplanets as of 2024, with thousands more awaiting confirmation. While some of these planets, such as those in the TRAPPIST-1 system, offer the tantalizing possibility of habitability, others have proven to be places of unimaginable extremes. Each of these hostile worlds tells a unique story about the diversity of planetary systems, challenging the notion of Earth-like conditions as the standard for habitability. One of the most striking aspects of these exoplanets is their diverse environmental challenges, which are shaped by factors like their proximity to their parent stars, the type of stars they orbit, and their geological and atmospheric compositions. For instance, planets orbiting red dwarf stars, which are cooler and smaller than our Sun, are often subjected to relentless stellar activity. These stars emit intense solar flares and bursts of X-ray and ultraviolet radiation, which can strip away planetary atmospheres and expose surfaces to harmful cosmic rays. This is the case for planets like Proxima Centauri b, located just 4.24 light-years away, making it the closest known exoplanet to Earth. Despite being in its star's habitable zone, the harsh radiation levels render it an inhospitable place. Another critical challenge lies in the gravity of these exoplanets, which can vary dramatically depending on their size and density. Some, like Kepler-10b, are classified as super-Earths and have significantly stronger gravitational forces than Earth. This increased gravity not only affects the physiology of potential human explorers, causing issues like increased cardiovascular strain and muscle fatigue, but also complicates the design of spacecraft and habitats. On the other hand, planets with weaker gravity, such as gas giants like WASP-121b, present their own set of challenges, including difficulties in retaining a stable atmosphere. The atmospheres of hostile exoplanets are another source of extreme danger. Many of these planets lack the protective atmospheric layers that shield life on Earth from harmful radiation and temperature fluctuations. For example, the exoplanet LHS 3844b has no atmosphere at all, leaving its surface exposed to cosmic rays and causing drastic temperature swings from scorching heat during the day to near absolute zero conditions at night. Other planets, such as HD 189733b, possess toxic atmospheres composed of gases like silicates and methane, which create environments where phenomena like glass rain and 2,000 miles per hour winds become terrifying realities. These atmospheres are not only hostile to life but also pose significant challenges for spacecraft, which must endure extreme pressures and corrosive conditions. Geological activity adds another layer of danger to these worlds. Many exoplanets, such as 55 Cancri e, are characterized by extreme volcanism, with surfaces dominated by vast oceans of lava and relentless seismic activity. The intense heat and instability make such planets nearly impossible to explore with current technology. Similarly, planets with strong tidal forces, caused by their proximity to their stars or the presence of multiple moons, can experience significant geological stress, leading to frequent earthquakes and volcanic eruptions. These conditions not only threaten the safety of any exploratory missions but also hinder the collection of accurate data. Extreme weather patterns further complicate the prospect of exploration. The most dramatic example of this is seen on WASP-33b, where wind speeds exceed 8,000 km per hour, creating sound patterns and atmospheric turbulence that would be deafening and disorienting to human explorers. On HAT P7b, the contrast between a perpetually illuminated day side and an eternally dark night side results in colossal heat storms, driven by the stark temperature differences. These storms can create high-altitude clouds of molten sapphire and ruby, a surreal yet deadly phenomenon. Such conditions not only create physical barriers to exploration but also have profound psychological effects on those who venture into these environments. The importance of understanding exoplanets goes beyond mere scientific curiosity. These distant worlds provide a critical context for studying the formation and evolution of planetary systems, including our own. By examining the extreme conditions on these planets, scientists can gain insights into the factors that contribute to habitability and the resilience of life. For instance, studying the effects of intense radiation on exoplanet atmospheres helps researchers understand how Earth's magnetic field and ozone layer have protected life over billions of years. Similarly, the geological and atmospheric processes observed on these hostile worlds offer a window into the dynamics that shaped Earth during its early history. Exoplanets, the planets that orbit stars outside our solar system, present some of the most extreme and varied environments known to humanity. From worlds with temperatures that can melt metal to those exposed to intense radiation, these planets provide an invaluable opportunity to test and develop the cutting-edge technologies and strategies needed for future space exploration. The unique challenges posed by these distant worlds, ranging from extreme temperatures to high radiation levels, not only push the boundaries of engineering and innovation but also offer lessons that can inform solutions to challenges on Earth, such as climate change and radiation exposure. Exploring these alien planets requires advancements in spacecraft shielding, autonomous robotic explorers, and sustainable life support systems. Moreover, these lessons can help us better understand how to adapt to extreme conditions here on Earth. One of the primary challenges in exploring exoplanets is their extreme environments, which demand innovations in engineering and technology. For instance, planets like WASP-121b, a hot Jupiter, experience scorching temperatures on their day side, reaching up to 2,500 degrees Celsius, 4,500 degrees Fahrenheit. For human or robotic exploration missions, developing materials and spacecraft capable of withstanding such heat is paramount. Advanced spacecraft shielding becomes essential to protect both the vehicle and its instrumentation from thermal damage. Current materials would degrade under such conditions, requiring the development of heat-resistant alloys or advanced insulation techniques that could prevent the spacecraft from overheating and ensure that its instruments remain functional. Exoplanets with high levels of radiation present another set of engineering challenges. Planets like Proxima Centauri b, which orbits a red dwarf star known for its intense solar flares, face extreme levels of ultraviolet, UV, and X-ray radiation. The radiation environment on these planets can strip away atmospheres and harm both biological systems and electronics. For space exploration, this means developing spacecraft with radiation shielding capable of blocking or mitigating the harmful effects of radiation, which can damage electronics, disrupt communications, and pose a risk to human health. Technologies such as multi-layer radiation shields, active magnetic fields to deflect radiation, and advanced materials that absorb or deflect radiation are likely to play an integral role in ensuring the safety and success of future space missions. Given the vast distances involved and the harsh environments of many exoplanets, human missions to these worlds are currently beyond our reach. Instead, autonomous robotic explorers will serve as the first line of exploration. These robots will be tasked with gathering data, performing surface scans, analyzing atmospheres, and collecting samples, often in environments that are too hostile for human presence. Robots designed for exoplanet exploration must be capable of operating independently over long periods. Autonomy will be key, as the immense distances between Earth and these planets result in communication delays, sometimes taking several minutes or even hours for signals to travel back and forth. This means that robotic explorers cannot rely on real-time control from Earth and must instead be equipped with air-driven systems that allow them to make decisions and adapt to unforeseen circumstances in real time. These robots will need to have advanced navigation systems, capable of operating in terrains that are often unpredictable and hostile, such as the molten lava surfaces of 55 Cancri E or the sapphire clouds of HAT P7b. One promising technology for autonomous exploration is machine learning, which could allow robotic explorers to process vast amounts of data and make decisions on the fly. For example, these robots could identify and navigate hazardous terrain, select appropriate landing sites, and prioritize scientific objectives based on real-time data. As we continue to develop more advanced AI and machine learning algorithms, robots will become more capable of operating in increasingly complex environments, reducing the need for human intervention and extending the range of our exploration efforts. For future human missions to exoplanets, the development of sustainable life support systems is crucial. These systems must be able to provide essential resources, such as air, water, food, and energy, in environments where these resources may be scarce or non-existent. Planets like LHS 3844b, which lacks an atmosphere, and TRAPPIST-1e, with potentially toxic gases in its atmosphere, require innovative solutions to ensure that astronauts can survive without the support of Earth's ecosystems. One of the most promising strategies for sustainable life support systems is closed-loop systems. These systems recycle air and water, creating a self-sustaining environment within the spacecraft or habitat. Bioregenerative life support systems, which use plants, algae, or microorganisms to filter CO2 and produce oxygen and food, could play a key role in long-term missions to exoplanets. For example, a hydroponic farm or aeroponics could be used to grow food in a soil-free environment, while algae could help filter carbon dioxide and provide oxygen. The challenge lies in designing systems that can function efficiently for extended periods without the need for resupply from Earth, especially in harsh exoplanetary conditions. In addition to recycling air and water, sustainable life support systems must also account for energy production. Since many exoplanets are located far from their stars or in environments where solar energy is limited, alternative energy sources will be required. Nuclear power, especially compact fission reactors, could provide a reliable source of energy for life support systems, communication, and scientific instruments. Advanced energy storage systems, such as high-capacity batteries or fuel cells, will also be essential to ensure a continuous power supply, even during periods when solar energy is unavailable. While the primary focus of exoplanet exploration is to understand other worlds, the technologies developed to explore these extreme environments also have significant applications here on Earth. For example, technologies designed to mitigate the effects of radiation in space could be adapted for use in environments with high levels of radiation, such as deep space missions, or even for improving radiation therapy for cancer patients. Similarly, the development of advanced materials to withstand extreme temperatures and pressure could find applications in industries such as aerospace, automotive engineering, and energy production. Furthermore, the closed-loop life support systems designed for space exploration could provide insights into improving resource management on Earth. These systems could be used in remote areas or in sustainable urban development, helping to create more efficient recycling systems for water, food, and energy. Technologies for growing food in space could revolutionize agriculture, particularly in regions with limited access to arable land, by promoting soil-free farming systems such as hydroponics and aquaponics. Finally, the lessons learned from extreme planetary environments can also inform strategies for addressing climate change. Studying how exoplanets with extreme conditions evolve, whether they lose their atmospheres due to solar radiation or develop greenhouse effects, can provide valuable insights into the processes driving climate change on Earth. Understanding how atmospheric and environmental factors contribute to a planet's habitability or destruction could help scientists develop more effective strategies for managing Earth's changing climate and protecting ecosystems from catastrophic shifts. Exoplanets serve as both a testing ground for future exploration technologies and a source of invaluable lessons for tackling some of Earth's most pressing challenges. The extreme conditions of these distant worlds push the boundaries of what is possible in spacecraft design, robotics, and life support systems. At the same time, the technologies developed to explore exoplanets offer insights that can help us address similar challenges on Earth, from managing radiation exposure to mitigating climate change. The exploration of exoplanets is not just about reaching the stars, it is about pushing the limits of human ingenuity, creating new solutions, and applying those lessons to make life on Earth more sustainable and resilient in the face of a changing world. The study of hostile exoplanets is also deeply intertwined with the search for extraterrestrial life. While these planets may seem inhospitable by Earth standards, they challenge our assumptions about the conditions necessary for life to exist. Recent discoveries of extremophiles, organisms that thrive in environments previously thought to be uninhabitable, have expanded the possibilities for life beyond Earth. Could microbes survive in the acidic clouds of Venus or in the icy crusts of Jupiter's moons? Similarly, could exotic forms of life adapt to the extreme conditions on exoplanets like Kepler-13b or 55 Cancri e? These questions drive researchers to explore the boundaries of biology and chemistry, seeking answers in the most unlikely places. Furthermore, hostile exoplanets serve as a reminder of the fragility of our own planet. The extreme conditions on these worlds highlight the delicate balance that makes Earth habitable, a balance that can be disrupted by natural or human-induced changes. Understanding the factors that lead to such hostile environments can help us better appreciate the importance of preserving Earth's unique ecosystems and addressing global challenges such as climate change. In the grand scheme of cosmic exploration, hostile exoplanets are both a warning and an opportunity. They caution us about the dangers that await beyond the safety of our solar system, but they also inspire us to push the boundaries of science and technology. The discovery of these worlds ignites a sense of wonder and curiosity, reminding us of humanity's innate desire to explore the unknown. As we continue to develop the tools and knowledge necessary to venture into these alien landscapes, we not only expand our understanding of the universe but also redefine what it means to be human. The journey to explore the scariest planets outside our solar system is not merely about overcoming challenges, it is about confronting the limits of our endurance, innovation, and imagination. These worlds, with their unyielding conditions and breathtaking extremes, are a testament to the diversity and complexity of the cosmos. They invite us to dream bigger, to ask deeper questions, and to strive for greater achievements in our quest to understand the universe and our place within it. As we stand at the precipice of interstellar exploration, these hostile exoplanets remind us of both the dangers and the rewards that come with venturing into the great unknown. Proxima Centauri b, located just 4.24 light-years away, is the closest known exoplanet to Earth. Discovered in 2016 by astronomers using the radial velocity method with the European Southern Observatory's HARPS spectrograph, this planet has captivated scientists and the public alike. Its proximity and the fact that it orbits within the habitable zone of its parent star, Proxima Centauri, have sparked discussions about its potential to support life and its role as a target for interstellar exploration. However, beneath its promising surface lies a host of challenges and dangers, making Proxima Centauri be one of the most intriguing yet formidable worlds discovered outside our solar system. Proxima Centauri b orbits a red dwarf star, the smallest and coolest type of star, with just 12% the mass and 14% the diameter of the Sun. Red dwarfs are fascinating celestial objects due to their abundance. They make up approximately 75% of the stars in the Milky Way, and their longevity, often burning for tens of billions of years. Despite their small size and relatively low luminosity, red dwarfs exhibit intense stellar activity. Proxima Centauri is no exception. It frequently emits powerful solar flares, bursts of energy that can be up to 10 times more intense than the strongest flares from the Sun. These flares are rich in X-rays and ultraviolet radiation, which can strip away the atmospheres of planets orbiting close to the star. Proxima Centauri b orbits its star at a distance of just 0.05 astronomical units, AU, about 5% of the Earth-Sun distance, completing one orbit in a mere 11.2 Earth days. This proximity places the planet well within the habitable zone, where temperatures could, in theory, allow for liquid water to exist. However, the close distance also exposes the planet to the intense radiation and stellar winds from Proxima Centauri. Over time, this bombardment could erode any atmosphere, leaving the surface unprotected from harmful cosmic rays. Despite these challenges, Proxima Centauri b's position in the habitable zone continues to fuel speculation about its potential for life, albeit life very different from what exists on Earth. A key factor influencing the conditions on Proxima Centauri b is its tidally locked nature. This means that one side of the planet constantly faces its star, experiencing perpetual daylight, while the other side remains in eternal darkness. This configuration creates extreme temperature disparities between the two hemispheres. On the day side, temperatures could soar to several hundred degrees Celsius, potentially vaporizing any surface water, while the night side could plunge to temperatures far below freezing. Such extremes pose significant challenges for habitability, as they create a harsh environment that makes the existence of stable, life-supporting conditions unlikely. However, some models suggest that a terminator zone, the narrow strip of land between the day and night sides, might offer a more temperate climate. In this region, the temperature gradients could potentially stabilize, allowing for the existence of liquid water. The possibility of a habitable terminator zone depends on the presence of an atmosphere capable of redistributing heat across the planet. Without such an atmosphere, the temperature extremes would likely render the planet barren and lifeless. Scientists continue to study the dynamics of tidally locked exoplanets to better understand whether such configurations can support habitable conditions. The solar flares from Proxima Centauri further complicate the prospects for habitability. These flares are so intense that they could strip away any existing atmosphere, especially if the planet lacks a strong magnetic field to deflect the charged particles. Even if Proxima Centauri b retained some of its atmosphere, the composition would likely be heavily influenced by the star's activity. For example, prolonged exposure to X-rays and ultraviolet radiation could break apart water molecules in the atmosphere, leading to the loss of hydrogen into space. This process, known as atmospheric escape, is a significant concern for planets orbiting red dwarfs. One of the most powerful flares observed from Proxima Centauri occurred in March 2016, shortly before the discovery of Proxima Centauri b. This flare increased the star's brightness by a factor of 14 in just minutes, emitting enough radiation to potentially sterilize the surface of the planet. Events like this raise questions about whether life could survive such conditions, even in subsurface environments shielded from direct exposure. The frequent and unpredictable nature of these flares highlights the challenges of habitability for planets orbiting active red dwarfs. The geological terrain of Proxima Centauri b remains a subject of speculation, as current technology cannot directly observe the planet's surface. However, based on its estimated mass of 1.17 Earth masses, it is likely a rocky planet, similar in composition to Earth. If the planet has retained some of its atmosphere and water, its surface could feature oceans, mountains, and valleys, shaped by geological processes like plate tectonics. Alternatively, if the planet has lost its atmosphere and water due to stellar activity, its surface could resemble that of Mars, with barren deserts, craters, and evidence of ancient water flows. The potential for volcanic activity on Proxima Centauri b adds another layer of complexity to its environment. Volcanism could play a crucial role in shaping the planet's surface and atmosphere, releasing gases that contribute to atmospheric composition and potentially creating transient habitable conditions. For instance, volcanic eruptions could release heat and chemical compounds that sustain microbial life in subsurface environments. However, excessive volcanic activity could also pose significant dangers, such as widespread lava flows and the release of toxic gases. The balance between these effects would depend on the planet's internal heat and geological history, factors that remain uncertain. Despite the challenges, Proxima Centauri b holds immense scientific and exploratory potential. Its proximity to Earth makes it an ideal candidate for future interstellar missions, such as the Breakthrough Starshot initiative, announced in 2016 by physicist Stephen Hawking, entrepreneur Yuri Milner, and other collaborators. This ambitious project aims to send a fleet of light-powered nanocraft to Proxima Centauri, traveling at speeds of up to 20% the speed of light. These tiny spacecraft would carry cameras and sensors to capture detailed images and data from Proxima Centauri b and its parent star, providing unprecedented insights into this intriguing world. Studying Proxima Centauri b is also crucial for understanding the broader context of planetary systems around red dwarfs. Given the abundance of red dwarfs in the galaxy, these stars likely host the majority of exoplanets, many of which could be in their habitable zones. By examining the challenges and possibilities of Proxima Centauri b, scientists can develop better models for assessing the habitability of similar planets. This research also informs the search for biosignatures, chemical markers that indicate the presence of life, on exoplanets with extreme environments. Proxima Centauri b is a world of contrasts and contradictions. Its proximity to Earth and position in the habitable zone make it a tantalizing target for exploration, yet its harsh environment and stellar activity highlight the challenges of finding life beyond our solar system. The planet's tidally locked nature creates a dramatic division between light and darkness, while its exposure to intense solar flares raises questions about the survival of any atmosphere or potential life. Despite these obstacles, Proxima Centauri b serves as a gateway to understanding the diversity of exoplanets and the resilience of life in the universe. It challenges us to rethink our definitions of habitability and inspires us to push the boundaries of exploration, seeking answers to the fundamental questions of our existence. Among the many remarkable exoplanets discovered in recent years, TRAPPIST-1e stands out as one of the most intriguing and promising candidates for further study. Located approximately 39.6 light-years away in the constellation Aquarius, TRAPPIST-1e is part of a 7-planet system orbiting the ultra-cool dwarf star TRAPPIST-1. This planetary system, discovered in 2017 using NASA's Spitzer Space Telescope and ground-based telescopes, represents a breakthrough in the search for Earth-like exoplanets. TRAPPIST-1e has captured the attention of scientists and space enthusiasts alike due to its position in the habitable zone, where liquid water might exist under the right conditions. Despite its potential, TRAPPIST-1e also presents a host of challenges that make it a hostile environment, testing the limits of habitability and human survival. The atmospheric composition of TRAPPIST-1e is one of the most critical factors in determining its habitability. While direct measurements of its atmosphere are not yet available, studies of exoplanet atmospheres in similar systems provide valuable clues. Due to its proximity to an ultra-cool dwarf star, TRAPPIST-1e's atmosphere could be shaped by the star's intense radiation and stellar winds. If the planet has managed to retain an atmosphere, its composition might differ significantly from Earth's, potentially containing high levels of toxic gases such as carbon dioxide, methane, or hydrogen sulfide. These gases, while potentially sustaining a greenhouse effect to keep the planet warm, could also create a hostile environment for human survival. The presence or absence of water vapor is another crucial aspect of TRAPPIST-1e's atmosphere. Water vapor is not only a key indicator of potential habitability but also plays a vital role in regulating surface temperatures. If TRAPPIST-1e lacks a substantial atmosphere or has lost its water due to stellar activity, its surface might resemble that of Mars, with dry, barren landscapes devoid of life-sustaining resources. On the other hand, if the atmosphere is too thick or contains excessive greenhouse gases, the planet might experience a runaway greenhouse effect, similar to Venus, where surface temperatures soar to uninhabitable extremes. TRAPPIST-1e faces significant challenges from ultraviolet, UV, and X-ray radiation, emitted by its parent star. Although TRAPPIST-1 is cooler and less luminous than the Sun, it is far more active, frequently producing flares that release bursts of high-energy radiation. These flares are capable of stripping away planetary atmospheres, especially if the planet lacks a strong magnetic field to shield it. Studies have shown that planets in close proximity to red and ultra-cool dwarfs are particularly vulnerable to this process, known as atmospheric escape. The loss of atmosphere would expose TRAPPIST-1e's surface to harmful cosmic rays and extreme temperature fluctuations, making the environment increasingly hostile over time. The X-ray radiation emitted by TRAPPIST-1 poses another serious threat. High-energy radiation can break apart molecules in the atmosphere, altering its chemical composition and potentially creating toxic byproducts. For instance, prolonged exposure to X-rays could deplete ozone layers, allowing dangerous UV radiation to reach the surface. Without the protection of an ozone layer or a magnetic field, life on TRAPPIST-1e would face significant challenges, even in subsurface environments, shielded from direct exposure. Another formidable obstacle to survival on TRAPPIST-1e is its severe weather conditions, which are likely influenced by the planet's tidally locked nature. Tidally locked planets, where one side permanently faces the star while the other remains in darkness, experience extreme temperature contrasts between their day and night sides. This dichotomy can drive powerful global wind systems and create turbulent weather patterns, with storms that could last for weeks or even months. The day side might endure constant heat, intense radiation, and high-speed winds, while the night side could plunge into perpetual freezing conditions. These extreme weather conditions could have catastrophic consequences for human survival. Winds reaching supersonic speeds would make surface exploration nearly impossible, while temperature swings between the day and night sides could pose significant challenges for maintaining stable habitats. Additionally, the potential for acidic rain or clouds composed of toxic gases could further complicate efforts to establish a human presence on TRAPPIST-1e. Even if the terminator zone, the narrow region between the day and night sides, offers relatively moderate conditions, the dynamic weather systems would likely disrupt any attempts to build long-term settlements. The lack of stable weather on TRAPPIST-1e underscores the importance of understanding the planet's atmospheric dynamics and developing strategies to adapt to its harsh environment. One potential solution involves building habitats in subsurface locations, such as caves or tunnels, which could shield inhabitants from extreme weather and radiation. These habitats would need to be equipped with advanced life support systems capable of recycling air and water, as well as maintaining stable temperatures. Additionally, robotic explorers and drones could play a vital role in scouting the planet's surface and gathering data on weather patterns, allowing scientists to identify safe zones for future missions. Magnetic shielding is another critical factor for survival on TRAPPIST-1e. On Earth, the magnetosphere protects the planet from harmful solar and cosmic radiation by deflecting charged particles from the Sun. If TRAPPIST-1e lacks a strong magnetic field, its surface would be exposed to intense radiation, making the development of artificial magnetic shielding essential for human habitation. Current research into magnetic field generators and radiation shielding materials could pave the way for technologies capable of protecting habitats and spacecraft on TRAPPIST-1e. Such innovations would not only ensure the safety of explorers but also provide valuable insights into the feasibility of colonizing other exoplanets with similar conditions. Despite these challenges, TRAPPIST-1e offers a unique opportunity to study the boundaries of planetary habitability and the potential for life beyond Earth. Its location in the habitable zone and its size, similar to that of Earth, make it an ideal candidate for further investigation. Upcoming missions, such as the James Webb Space Telescope and next-generation observatories, will provide detailed information about TRAPPIST-1e's atmosphere, surface conditions, and potential biosignatures. By studying this planet, scientists hope to gain a deeper understanding of how planets evolve in hostile environments and what factors contribute to the emergence and sustainability of life. TRAPPIST-1e is more than just a scientific curiosity, it is a testament to the resilience of planetary systems and the diversity of worlds in our galaxy. While its challenges, ranging from toxic atmospheres and radiation to severe weather and the absence of magnetic shielding, make it an incredibly hostile place, they also highlight the ingenuity required to explore and potentially adapt to such environments. In the quest to understand TRAPPIST-1e, humanity is not only advancing the frontiers of knowledge but also laying the groundwork for future interstellar exploration and the search for life in the cosmos. This mysterious and formidable world reminds us of the vast possibilities that lie beyond our solar system, and the enduring spirit of discovery that drives us to explore the unknown. Among the many exoplanets discovered in recent decades, TRES-2b, located approximately 750 light-years away in the constellation Draco, is one of the most enigmatic and unsettling. Identified in 2006 using the transit method by NASA's Kepler Space Telescope, TRES-2b is classified as a hot Jupiter, a gas giant similar in size to Jupiter but orbiting much closer to its parent star. Its most striking and eerie characteristic, however, is its uniquely dark atmosphere, which absorbs over 99% of the light that falls on it, making it the darkest known exoplanet in the universe. This feature, combined with its extreme conditions, has earned TRES-2b a reputation as one of the most inhospitable and mysterious planets outside our solar system. TRES-2b's incredibly dark atmosphere is the result of its unique chemical composition. Unlike Jupiter, which reflects about 34% of the sunlight that reaches it due to the presence of ammonia clouds, TRES-2b lacks such reflective materials. Instead, its atmosphere is dominated by gases such as titanium oxide, vaporized sodium, and potassium, which are highly effective at absorbing visible light. This absorption, combined with the planet's close proximity to its parent star, creates an oppressive, lightless environment. The planet's surface appears eerily black, interrupted only by a faint red glow caused by thermal radiation from its intensely heated atmosphere, where temperatures can reach up to 1,100 degrees Celsius, 2,000 degrees Fahrenheit. This glow resembles the dim embers of a dying fire, adding to the planet's haunting visual presence. The psychological impact of such perpetual darkness on human explorers would be profound. Darkness is often associated with fear, uncertainty, and isolation, and extended exposure to such an environment can lead to conditions like seasonal affective disorder, SAD, depression, and cognitive impairments. On Earth, Light plays a crucial role in regulating the circadian rhythm, the internal biological clock that governs sleep, energy levels, and overall mental health. Without access to natural light, explorers on Tres 2b would need artificial lighting systems that not only provide illumination, but also mimic the spectrum and intensity of sunlight to maintain physiological and psychological well-being. In addition to the challenges posed by its darkness, Tres 2b is tidally locked, meaning that one side of the planet permanently faces its parent star while the other side remains in eternal night. This creates extreme temperature disparities between the two hemispheres. On the day side, temperatures soar to levels that can vaporize metals, while the night side plunges into frigid cold, possibly approaching absolute zero. The absence of atmospheric circulation capable of efficiently redistributing heat between the two sides further exacerbates these extremes, making the planet even more hostile to any form of life or exploration. For humans, navigating such an environment would require advanced technology capable of withstanding both the searing heat and the bone-chilling cold, as well as equipment designed to operate in the absence of thermal stability. Another significant challenge posed by Tres 2b is its limited light, which complicates the generation of energy and the production of food. Solar power, a primary energy source for space missions, would be severely constrained due to the planet's lack of reflective surfaces and minimal light intensity on the night side. This limitation necessitates the development of alternative energy sources, such as nuclear power or advanced battery systems, capable of sustaining operations in such a dark and extreme environment. Additionally, the production of food through methods like hydroponics or aeroponics, which rely on artificial lighting to simulate sunlight, would require highly efficient lighting systems tailored to the planet's conditions. These systems would need to balance energy consumption with output, ensuring that plant growth and human sustenance are maintained in a resource-scarce setting. The perpetual darkness on Tres 2b also presents unique challenges for exploration and settlement. Navigation in such an environment would require sophisticated technologies, including LiDAR systems, infrared imaging, and autonomous robotics capable of mapping the terrain and identifying hazards in the absence of visible light. Human explorers would need advanced night vision systems or augmented reality interfaces that enhance visibility in low light conditions while conserving energy. Habitats designed for Tres 2b would need to prioritize insulation and thermal regulation, as well as incorporate adaptive lighting systems to create a sense of normalcy for inhabitants. Despite these challenges, Tres 2b provides a unique opportunity to test and develop technologies for surviving in extreme environments. Its oppressive darkness and temperature extremes make it a valuable analog for studying the limits of human resilience and adaptability. The lessons learned from exploring Tres 2b could have applications beyond exoplanetary research, such as improving technologies for deep-sea exploration, polar expeditions, or long-duration missions to dark and isolated environments, such as the Moon's permanently shadowed craters or the subsurface oceans of icy moons like Europa and Enceladus. Moreover, Tres 2b's unusual characteristics raise important questions about the diversity and formation of planetary systems. The planet's proximity to its parent star challenges conventional models of gas giant formation, as such planets are thought to form far from their stars and migrate inward over time. Understanding how Tres 2b and similar hot Jupiters maintain their dark atmospheres and extreme conditions could provide insights into the chemical and physical processes that shape exoplanetary environments. The study of Tres 2b, one of the darkest known exoplanets, offers crucial insights not only into the nature of extreme planetary environments, but also into the search for life beyond Earth. Despite the planet's inhospitable conditions, with its unique ability to absorb over 99% of the light that reaches it, Tres 2b serves as an important case study for understanding how extreme environments can impact the potential for life and the methods we use to detect it. While Tres 2b is unlikely to host life due to its extreme heat and radiation exposure, its study underscores the importance of considering a wide range of environmental factors when assessing other planets for biosignatures, signs of life. One of the key characteristics of TRES-2b is its dark atmosphere, which poses significant challenges for detecting subtle signs of life or organic processes. The planet's atmosphere absorbs nearly all the visible light from its parent star, giving it a unique black appearance. This extreme darkness could make it difficult for telescopes and instruments to detect the usual spectral signatures that indicate the presence of certain chemical compounds, such as water vapor, methane, or oxygen, that might suggest biological activity. In other words, the very characteristic that makes TRES-2b so interesting as an exoplanet also complicates our ability to study it for signs of life. If life were to exist on TRES-2b, or on any similar exoplanet, the faint signals it produces could easily be masked by the overwhelming darkness, making it much harder to identify biosignatures using traditional observation methods. This difficulty in detecting signs of life in extremely dark environments has broad implications for the search for life on other exoplanets, especially those that are similarly obscure or challenging to observe. As scientists continue to refine their methods of detecting atmospheric chemistry and other signs of life on exoplanets, they must develop techniques capable of uncovering subtle emissions and chemical markers that are not immediately apparent in the usual light spectra. For example, TRES-2b could hide potential traces of organic chemicals beneath the thick, light-absorbing layers of its atmosphere, requiring instruments that can analyze atmospheric composition in novel ways, such as through infrared or radio frequency spectroscopy. The challenge presented by TRES-2b's darkness exemplifies a larger issue faced by astronomers studying exoplanets: how to detect and analyze faint emissions that might indicate life or biological processes. Many biosignatures on Earth, such as carbon dioxide, oxygen, and methane, are often present in large quantities because they are actively cycled in the atmosphere by life forms. However, on planets with extreme conditions, such as those with dense clouds, low reflective surfaces, or minimal sunlight, these signatures could be far less pronounced, requiring more advanced instruments and techniques to detect them. Researchers will need to develop next-generation telescopes and spectrometers that can distinguish and isolate these faint signals even when they are submerged in a sea of background noise. The extreme darkness of TRES-2b also brings attention to the broader concept of thermal emissions, radiation emitted by a planet due to its temperature. On planets with temperatures as high as those on TRES-2b, thermal emissions may be the most significant way to detect the presence of atmospheric compounds. However, the planet's high temperatures and extreme radiation levels may interfere with thermal readings, potentially masking important signals of atmospheric chemistry or even any potential organic activity. As the technology improves, space telescopes such as James Webb will likely be tasked with capturing higher resolution infrared spectra that can reveal otherwise obscured emissions. These advancements are necessary not only for exoplanetary exploration, but also for enhancing our understanding of the physical and chemical processes that govern planets in harsh environments. Additionally, the study of planets like TRES-2b emphasizes the importance of diversity in exoplanet environments. While scientists often focus on planets located in the habitable zone, the region around a star where liquid water can exist, TRES-2b's extreme conditions highlight how biosignatures could exist in environments far outside the typical boundaries of habitability. Life, as we know it, requires certain conditions, such as water, but exploring a wider range of environments, including those with intense heat, radiation, or darkness, challenges our preconceptions about the limits of life. Understanding how to detect biosignatures in such harsh conditions can open up new avenues for identifying life in environments that were once thought to be completely uninhabitable. In essence, the study of TRES-2b underscores the need for a broadening of our search criteria when considering the potential for life beyond Earth. While the planet itself is unlikely to harbor life, its extreme nature offers a crucial learning opportunity for future missions to other exoplanets. The development of advanced technologies capable of detecting weak signals in extreme conditions will not only improve our chances of discovering biosignatures on planets like TRES 2b but will also expand our understanding of how life might exist in a variety of environments across the universe. While TRES 2b's extreme darkness and inhospitable environment suggest that it is unlikely to support life, the challenges it presents in detecting biosignatures serve as a reminder of the complexity of life's potential across the cosmos. The lessons learned from studying such planets will be crucial in refining our search for life on exoplanets, pushing the boundaries of technology, and expanding our understanding of the diverse environments in which life might thrive. As exoplanetary exploration continues to advance, the ability to detect and analyze faint signs of life in these extreme conditions will remain one of the most exciting and important frontiers in the quest to answer one of humanity's oldest questions: are we alone in the universe? TRES 2b is a planet of extremes, defined by its uniquely dark atmosphere, temperature disparities, and the profound challenges it poses for exploration and survival. Its perpetual darkness not only tests the limits of human psychology but also forces us to innovate new technologies for navigating and sustaining life in such hostile environments. As a subject of scientific inquiry, TRES 2b expands our understanding of planetary diversity and resilience, pushing the boundaries of what we consider habitable or even explorable. It serves as a stark reminder of the vast and varied nature of the cosmos, where the unexpected and the unimaginable often coexist, challenging us to confront the unknown with curiosity and determination. Kepler-10b, located approximately 560 light-years away in the constellation Draco, holds the distinction of being the first rocky exoplanet confirmed by NASA's Kepler Space Telescope in 2011. Its discovery marked a milestone in the search for terrestrial planets outside our solar system, providing astronomers with a valuable opportunity to study the characteristics of Earth-like planets in extreme environments. Despite its rocky composition, Kepler-10b is a world of relentless hostility, with conditions so extreme that it has been likened to a furnace in space. The planet's intense heat, lack of atmosphere, and formidable geological features present significant challenges to exploration and survival, making it one of the most inhospitable planets discovered to date. The most defining feature of Kepler-10b is its furnace-like environment, where temperatures soar to an estimated 2,500 degrees Celsius, 4,500 degrees Fahrenheit, on the day side. This extreme heat is a direct result of the planet's proximity to its parent star, a Sun-like star known as Kepler-10. Kepler-10b orbits at a distance of just 0.016 astronomical units, AU about 16 times closer to its star than Mercury is to the Sun, completing one orbit in a mere 20 hours. At such a close distance, the planet is subjected to intense stellar radiation, creating conditions where even metals like iron and rock can melt and vaporize. This searing heat makes the presence of liquid water on Kepler-10b virtually impossible. Water, if it ever existed on the planet, would have boiled away long ago, leaving behind a barren, desiccated surface. The lack of water also means that any processes required to sustain life as we know it cannot occur. Moreover, the extreme temperatures likely prevent the formation of a breathable atmosphere. Even if the planet once had an atmosphere, the intense radiation from its star would have stripped it away over time, exposing the surface to the vacuum of space. This absence of an atmosphere exacerbates the already harsh conditions, as it leaves the planet without a protective layer to moderate temperatures or shield it from cosmic and solar radiation. Kepler-10b's geological features further add to its challenges. The planet's surface is likely covered in molten lava on the day side, where temperatures are high enough to sustain vast oceans of liquid rock. As the molten material cools and solidifies while being pulled by the planet's strong gravity, it may form jagged terrains and sharp ridges. Dust and fine particles from volcanic or impact activity could also settle on the surface, creating hazards for exploration equipment and spacecraft. The night side, while cooler than the day side, is still an unwelcoming environment, likely dominated by hardened lava plains and sharp, rocky outcrops. This extreme topography would make landing and navigation extraordinarily difficult for robotic or human explorers. Adding to these challenges is Kepler-10b's intense gravity, which is nearly twice as strong as Earth's due to the planet's high density and relatively large mass. While Kepler-10b is slightly smaller than Earth, with a radius of about 1.4 times that of Earth, its rocky composition contributes to its greater mass. This stronger gravitational pull would have profound effects on exploration efforts. Human explorers, for example, would experience increased strain on their muscles, bones, and cardiovascular systems, leading to rapid fatigue and potential long-term health risks. For spacecraft and landing modules, the higher gravity would require significantly more energy to achieve liftoff, complicating missions that involve surface exploration or sample return. The high gravity would also influence the behavior of geological processes on the planet. For instance, landslides and volcanic eruptions might occur more frequently and with greater force due to the increased gravitational pull. Dust and debris from such events would settle more quickly, creating layers of compacted material that could obscure the planet's geological history. Understanding these processes is essential for interpreting the composition and evolution of rocky exoplanets like Kepler-10b, which could provide clues about the formation of planets in extreme conditions. Despite its inhospitable nature, Kepler-10b offers unique opportunities for scientific research. Its rocky composition makes it a valuable analog for studying the interiors of terrestrial planets, particularly under conditions of extreme heat and pressure. The planet's close proximity to its star provides a natural laboratory for understanding the effects of stellar radiation on planetary surfaces and atmospheres. By studying Kepler-10b, scientists can gain insights into the processes that govern planetary formation and evolution in high-energy environments, as well as the factors that contribute to atmospheric loss and surface transformation. Kepler-10b's discovery has also advanced the development of technologies used to detect and characterize rocky exoplanets. The techniques refined during its study, such as the transit photometry method used by the Kepler Space Telescope, have since been applied to identify thousands of other exoplanets, including those in more temperate zones. Additionally, the planet serves as a benchmark for understanding the diversity of rocky worlds in the galaxy, highlighting the range of conditions under which planets can form and exist. Exploration of Kepler-10b, while challenging, would require innovative technologies and strategies. For instance, robotic landers equipped with advanced thermal shielding and heat-resistant materials could be deployed to study the planet's surface. These landers would need to withstand extreme temperatures and gravitational forces while collecting data on the planet's geology and composition. Instruments capable of operating in high radiation environments, such as spectrometers and seismometers, could provide valuable information about the planet's interior and surface processes. Human exploration of Kepler-10b, though unlikely with current technology, would require significant advancements in life support systems and protective gear. Habitats designed for such an environment would need to be fully sealed and insulated, with systems capable of maintaining stable internal temperatures and filtering out hazardous particles. Energy generation would pose another challenge, as solar panels might not function efficiently in such a high radiation environment. Alternative energy sources, such as nuclear reactors or advanced fuel cells, would likely be necessary to power habitats and equipment. The study of Kepler-10b also has implications for the search for life beyond our solar system. While the planet itself is unlikely to host life, its extreme conditions push the boundaries of what we consider habitable. By examining the factors that make Kepler-10b uninhabitable, scientists can refine their criteria for identifying planets with the potential to support life. This research also contributes to our understanding of planetary systems as a whole, shedding light on the complex interplay between a planet's composition, orbit, and stellar environment. Kepler-10b stands as one of the most extreme exoplanets discovered, offering a vivid example of the harsh environments that exist beyond our solar system. This rocky planet, located approximately 560 light-years away in the constellation Draco, is a world defined by a combination of furnace-like temperatures, lack of atmosphere and water, and challenging geological features. Its intense gravitational forces, coupled with its proximity to its star, make it one of the least hospitable places for life, yet an invaluable subject for scientific inquiry. Although it is an unlikely destination for human settlement, Kepler-10b holds immense potential for advancing our understanding of planetary formation and evolution, particularly in high-energy environments. Kepler-10b's close proximity to its host star contributes to its furnace-like temperatures, reaching up to 1,800 degrees Celsius, 3,272 degrees Fahrenheit, on its day side. The planet orbits its star in just 0.84 Earth days, a speed that places it closer to its star than Mercury is to the Sun, making it one of the hottest exoplanets discovered. The extreme heat is so intense that it has likely led to the vaporization of any atmosphere, leaving the planet exposed to the harsh conditions of deep space. With a surface temperature high enough to melt many metals, Kepler-10b becomes a prime example of an environment where liquid water could never exist, further diminishing the likelihood of biological activity. The absence of an atmosphere means the planet has no protection against the harsh radiation from its parent star, making it a world where no known form of life could survive. Additionally, this lack of atmosphere exacerbates the temperature extremes between the planet's day and night sides, creating an environment where extreme heat contrasts sharply with the cold darkness of the planet's night side. The geological features of Kepler-10b add another layer of complexity to its already hostile environment. The planet's surface, which likely consists of solid rock, is subjected to extreme forces from the intense gravitational pull of its star. The planet's surface is likely to be volatile, possibly dominated by large-scale volcanic activity, with lava flows constantly reshaping its surface. The planet's geological instability, compounded by its extreme temperatures and lack of atmosphere, means that the surface is in a constant state of flux. Such an environment is incredibly difficult to study, as any probes or landing missions would have to contend with constantly changing surfaces and the risk of equipment failure due to extreme heat and radiation exposure. Additionally, Kepler-10b's gravitational forces are also quite extreme. Despite being about 1.4 times the size of Earth, the planet is denser, which leads to a higher gravitational pull. This intense gravity creates challenges not only for any potential landing missions but also for the potential future study of the planet's surface, which would be difficult to navigate with robotic explorers or, in the case of human missions, hazardous to astronaut health. The increased gravity would require explorers to contend with higher stress on their bodies, leading to challenges in mobility and long-term sustainability. Despite its extreme and inhospitable nature, Kepler-10b provides invaluable insights into planetary formation and the evolution of rocky exoplanets. As one of the first confirmed rocky exoplanets, it has served as a key object of study in the search for other Earth-like worlds. The study of Kepler-10b's geological processes, including its high temperatures and the interaction between its surface and the radiation from its star, helps astronomers understand the ways in which rocky planets form and evolve. For instance, the fact that Kepler-10b is so close to its star and has likely lost its atmosphere suggests that it may have formed far from its star and migrated inward over time, a process that could apply to other planets in similar systems. Kepler-10b's conditions make it an example of a planet that is far beyond the traditional habitable zone, the region around a star where conditions are favorable for liquid water to exist. This characteristic makes Kepler-10b a useful contrast to planets that are considered potential candidates for habitability. By studying extreme exoplanets like Kepler-10b, scientists can better understand the limits of habitability, what makes a planet habitable, and how certain planets evolve in environments that are very different from Earth's. While Kepler-10b is unlikely to be a place where humans can ever settle, its extreme conditions present opportunities for pushing the boundaries of space exploration. Studying how planets in such high-energy environments form, evolve, and behave can provide key information for future missions to other rocky exoplanets. The development of spacecraft and exploration technology capable of withstanding extreme heat, radiation, and gravitational forces will be essential for future missions to these distant worlds. Technologies such as thermal shielding, radiation-resistant materials, and advanced robotic systems are essential for understanding planets like Kepler-10b, even if humans may never be able to physically visit such planets. Kepler-10b's extreme environment provides a natural testing ground for these technologies, offering lessons that can be applied to other missions within our solar system. The technologies developed to explore these exoplanets will likely find applications for deep space exploration, with lessons learned helping to shape how we approach missions to other distant worlds, including the moons of Jupiter and Saturn, or even future interstellar exploration. Kepler-10b also serves as a powerful reminder of the diversity and complexity of planetary systems beyond our own. Its extreme conditions force us to broaden our understanding of how planets can form and evolve, reminding us that the universe is far more diverse than Earth-like planets or those in the habitable zone. Kepler-10b's existence challenges us to reconsider what makes a planet unique and how different worlds can offer profound insights into the processes of planetary formation, geology, and atmospheric evolution. In this way, Kepler-10b inspires curiosity and innovation, spurring scientific discovery and technological progress. While it may not be a place for humans to settle, its study encourages exploration, pushing scientists to devise new ways to investigate planets in extreme conditions. As we continue to study worlds like Kepler-10b, we expand our knowledge of the cosmos, advancing our technology and our understanding of what is possible in space exploration. These discoveries continue to drive innovation, providing the tools needed to venture further into the universe. Kepler-10b is a planet of extremes, defined by its furnace-like temperatures, lack of atmosphere, challenging geological features, and intense gravitational forces. While it remains a daunting target for exploration, its conditions offer valuable opportunities to study the formation and evolution of rocky planets under high-energy environments. As a pioneer among rocky exoplanets, Kepler-10b serves as an important reminder of the diversity and complexity of worlds beyond our solar system. It challenges us to expand our understanding of the universe and our place within it, pushing the boundaries of what we know about the cosmos. Although Kepler-10b may never be a destination for human settlement, it continues to inspire curiosity, driving innovation and exploration as we reach ever further into the stars. Among the numerous exoplanets discovered outside our solar system, HD 189733b stands out as one of the most violently inhospitable. Located approximately 64 light-years away in the constellation Vulpecula, this hot Jupiter has been studied extensively since its discovery in 2005 using the radial velocity method. HD 189733b is a gas giant, similar in size to Jupiter but orbiting extremely close to its parent star, completing a full orbit in just 2.2 Earth days. Its extreme proximity to its star subjects it to intense heat and radiation, creating a hellish environment characterized by raging storms, high-speed winds, and unique atmospheric phenomena. These factors make HD 189733b a prime example of a truly alien world, offering insights into the diverse and violent conditions that can exist on exoplanets. One of the most striking and terrifying features of HD 189733b is its glass rain, a phenomenon driven by the planet's extreme atmospheric conditions. The planet's atmosphere contains silicate particles, which, under the high temperatures of the day side, reaching up to 1200 degrees Celsius, 2200 degrees Fahrenheit, can condense into small droplets of molten glass. These droplets are carried by the planet's ferocious winds, which whip through the atmosphere at speeds exceeding 5,400 miles per hour, 8,700 kilometers per hour, nearly 7 times the speed of sound. As a result, shards of glass rain sideways, propelled by these supersonic winds, creating a lethal environment for any potential exploration. The glass rain not only highlights the extreme chemical processes at work but also demonstrates how alien and hostile the weather on exoplanets can be. The violent storms on HD 189733b are another key hazard, driven by the planet's tidally locked nature. One side of the planet faces its star permanently, enduring relentless heat, while the other side remains in perpetual darkness, experiencing much cooler temperatures. This stark temperature difference generates extreme thermal gradients, fueling the planet's massive storm systems. The winds on HD 189733b are some of the fastest ever observed, circulating the planet in just a few hours and redistributing heat between the day and night sides. These winds are not only powerful but also chaotic, creating turbulence that disrupts the atmosphere on a planetary scale. The high-speed winds and extreme temperature shift present significant challenges for any theoretical human exploration. The day side of HD 189733b is subjected to scorching heat, while the night side experiences much colder conditions, creating a dynamic and unpredictable environment. The rapid wind speeds would make it nearly impossible for any spacecraft or lander to remain stable, let alone conduct meaningful research. Furthermore, the extreme pressure and temperature variations in the atmosphere would pose significant risks to both equipment and potential explorers, requiring advanced technology capable of withstanding these conditions. Protective materials, adaptive spacecraft designs, and real-time monitoring systems would be necessary to navigate such a hostile world. Another unique aspect of HD 189733b is the formation of silicate clouds, which play a critical role in the planet's extreme weather. Silicate particles in the atmosphere condense under specific temperature and pressure conditions, forming clouds that reflect blue light, giving the planet its striking cobalt blue appearance when observed from space. These clouds are highly dynamic, driven by the planet's intense winds and thermal gradients. On the day side, the heat causes the clouds to vaporize, while on the night side, cooler temperatures allow them to condense. This constant cycling of silicate clouds contributes to the planet's turbulent atmospheric currents, amplifying the severity of its storms and creating conditions unlike anything seen in our solar system. The presence of silicate clouds and their interaction with the planet's extreme heat and winds also raises questions about the broader implications of such weather systems. On Earth, clouds play a vital role in regulating temperature and driving the water cycle, but on HD 189733b, they create a feedback loop that intensifies the planet's hostility. The silicate particles can absorb and scatter radiation, affecting the atmospheric dynamics and potentially altering the planet's thermal structure over time. Studying these processes provides valuable insights into how extreme weather systems evolve on exoplanets and how they differ from those on Earth. The implications of turbulent atmospheric currents for human exploration are profound. The constant churning of HD 189733b's atmosphere would make it extraordinarily difficult to deploy instruments or conduct studies, as any probe or spacecraft would be subjected to relentless forces. Additionally, the chemical composition of the atmosphere, which includes hydrogen, methane, and silicate particles, poses further challenges. These gases and particles could corrode or damage equipment, necessitating the development of advanced materials capable of withstanding both chemical and physical stresses. For human explorers, the conditions would be even more prohibitive, requiring life support systems capable of operating in an environment with no solid surface, extreme pressure, and temperatures that fluctuate dramatically across the planet. Despite its hostility, HD 189733b offers an incredible opportunity for scientific exploration. The planet's unique weather patterns and chemical processes provide a natural laboratory for studying the physics of extreme atmospheres. By examining the interaction between silicate clouds, thermal gradients, and supersonic winds, scientists can gain a better understanding of how weather systems function on gas giants and other exoplanets. These studies also have implications for planetary science within our solar system, as they can inform models of atmospheric dynamics on worlds like Jupiter, Saturn, and their moons. The study of HD 189733b also highlights the diversity of planetary environments in the galaxy. While the planet is uninhabitable by any standard, it serves as a reminder of the wide range of conditions that can exist on exoplanets. Understanding these extremes is crucial for refining our search for habitable worlds, as it allows scientists to identify the factors that make a planet more or less conducive to life. HD 189733b's dynamic and violent nature challenges traditional notions of what a planet can be, expanding the boundaries of planetary science and exploration. HD 189733b is one of the most extreme and fascinating exoplanets discovered to date, offering a glimpse into the complex and volatile nature of distant worlds. This exoplanet is known for its intense and harsh atmospheric conditions, which include glass rain, violent storms, high-speed winds and silicate clouds, all of which contribute to its reputation as one of the most hostile environments outside our solar system. The planet orbits its host star, a bright and active K-type star, at a distance that places it far too close to its star to be anything resembling Earth-like. As a result, HD 189733b experiences turbulent atmospheric currents and extreme weather patterns that would be impossible for humans to endure, but incredibly valuable for understanding planetary weather systems and the forces that shape them. The most remarkable and unique characteristic of HD 189733b is its glass rain. The planet's atmosphere is composed of silicate particles that, under the influence of the planet's intense heat, are vaporized into gas and then condense into molten glass droplets. These droplets are carried by high-speed winds, reaching speeds of up to 5,400 miles per hour, 8,700 kilometers per hour, making it one of the fastest wind speeds observed on any exoplanet. As a result, the glass rain is not a soft, gentle fall of water droplets but instead a dangerous, sideways rain of molten glass. The high-speed winds that carry the glass droplets make the planet's surface utterly inhospitable, as even advanced equipment or human explorers would be subjected to the abrasive and destructive effects of this phenomenon. These extreme conditions raise important questions about how planetary atmospheres evolve in the presence of such high-energy environments and what it might take to study them effectively, even remotely. In addition to glass rain, the planet experiences violent storms that can cover vast portions of the planet's surface. These storms, driven by the extreme temperature gradients between the day and night sides of the planet, churn the atmosphere in a perpetual state of upheaval. Due to the planet's tidally locked nature, where one side constantly faces the star and the other remains in permanent darkness, the temperature differences between the day and night sides are extreme. This stark division of heat creates a high level of atmospheric instability, driving massive storms that would make any attempt at surface exploration incredibly dangerous. These storms contribute to the planet's chaotic weather systems, constantly altering the composition of its atmosphere and reinforcing the planet's status as a tumultuous world. Another feature of HD 189733b's atmosphere is its silicate clouds, which form as a result of the high temperatures and the presence of vaporized silicates in the atmosphere. These clouds, like the glass rain, are part of the planet's unique chemistry and play a crucial role in its weather systems. Silicate clouds are often seen on Earth as a result of volcanic activity, but on HD 189733b, they form naturally as part of the ongoing chemical processes driven by the planet's extreme conditions. The interaction between these clouds and the high-speed winds contributes to the formation of intense weather patterns, creating a feedback loop that intensifies the planet's atmospheric currents and storm activity. Studying these clouds and their behavior can provide critical insights into the formation of clouds and weather systems on other planets, particularly those with high temperatures and dynamic atmospheres. These turbulent and extreme conditions on HD 189733b push the limits of our understanding of planetary weather systems. The planet's violent atmospheric behavior, driven by both its proximity to its star and its unique chemical composition, offers a laboratory for studying the interactions between temperature, chemistry, and weather. The presence of glass rain and silicate clouds challenges our preconceptions of what types of atmospheric phenomena are possible, broadening our perspective on the diversity of exoplanetary environments. These extreme weather patterns also provide an opportunity to study the mechanisms behind planet-wide storm systems, including how energy is transferred within an atmosphere and how planetary surfaces are shaped by such intense forces. While HD 189733b remains an inhospitable environment for human life, its study is critical for our understanding of exoplanetary atmospheres and planetary science. By investigating the extreme weather systems on HD 189733b, scientists can gain insights into the types of conditions that might exist on other exoplanets, some of which may lie within the habitable zone, the region around a star where liquid water could potentially exist. Understanding the complexity of weather systems on hostile exoplanets like HD 189733b helps refine our models for identifying planets that could host life or those that, like HD 189733b, may be completely unsuitable for habitation. HD 189733b also serves as a reminder of the boundless possibilities that exist in the universe. The diversity of exoplanets, with their extreme conditions and unique characteristics, expands the boundaries of our understanding of what is possible in the cosmos. While planets like HD 189733b may never be a target for human settlement, their study offers invaluable insights into the forces that shape planets and their atmospheres, helping us better understand how planetary systems evolve and what factors contribute to their habitability. In this way, even the most extreme exoplanets can play a crucial role in advancing scientific knowledge and technological innovation. HD 189733b is a planet defined by its glass rain, violent storms, high-speed winds, and silicate clouds, all of which contribute to its position as one of the most extreme and fascinating exoplanets discovered. Its turbulent atmosphere and extreme conditions offer both challenges and opportunities for scientific exploration, pushing the boundaries of our understanding of planetary weather systems and chemical processes. While human exploration of HD 189733b is currently impossible, the insights gained from studying its environment are invaluable for expanding our knowledge of the universe, reinforcing the complexity and diversity of exoplanets, and inspiring curiosity and innovation as we continue to push the limits of space exploration. WASP 121b, located approximately 850 light-years away in the constellation Puppis, is a planet of extremes. Discovered in 2015 using the transit method, this hot Jupiter has become one of the most studied exoplanets due to its proximity to its host star and the remarkable phenomena occurring in its atmosphere. With its orbit so close to its star that it completes a revolution in just 1.27 Earth days, WASP 121b experiences some of the harshest conditions imaginable. From molten metals in its atmosphere to the effects of tidal forces and radiation, WASP 121b provides an unparalleled glimpse into the extremes of planetary science. These conditions not only make the planet an object of scientific curiosity but also highlight the unimaginable challenges it would pose to exploration or survival. One of the most striking and hazardous features of WASP 121b is the presence of molten metals in its atmosphere. The planet's day side reaches temperatures exceeding 2,500 degrees Celsius, 4,500 degrees Fahrenheit, which is hot enough to vaporize metals such as iron and magnesium. These metals, in gaseous form, are carried to the upper atmosphere, where they can condense into clouds of molten droplets under certain conditions. Observations made using the Hubble Space Telescope have detected these metallic signatures, confirming that WASP 121b's atmosphere hosts chemical processes unlike anything seen on Earth. The risks associated with such an environment are profound. The molten metals in the atmosphere pose a significant threat to any equipment or exploratory mission, as their corrosive properties could damage spacecraft materials, even those designed for extreme environments. Moreover, the presence of vaporized metals adds to the planet's reflectivity, creating a blindingly bright day side that would complicate both visual navigation and sensor-based data collection. Any potential explorers would need to account for the destructive effects of molten metal rain, a phenomenon that challenges even the most advanced engineering solutions. Another key factor shaping WASP-121b's environment is the impact of tidal forces and thermal shock. The planet is so close to its host star that it is experiencing tidal heating, a process in which gravitational interactions stretch and compress the planet's interior, generating immense amounts of heat. These tidal forces have deformed WASP-121b into an oblong, football-like shape, with its atmosphere bulging outward toward the star. This deformation exacerbates the already extreme temperature disparities between the day and night sides, leading to thermal shock as materials on the planet's surface and in its atmosphere are rapidly heated and cooled. These tidal interactions also contribute to the planet's volatile atmosphere, driving winds that can reach supersonic speeds and carry heat and material from the day side to the night side. The night side, while cooler, is still inhospitable, with temperatures that can condense vaporized materials into molten rain. The constant stretching and compression of the planet due to tidal forces, combined with the dramatic thermal gradients, create a dynamic and unstable environment that would be extraordinarily challenging for any exploratory mission to navigate. WASP-121b's close proximity to its host star further compounds its hostility due to the radiation challenges posed by intense stellar activity. Orbiting at a distance of just 0.025 astronomical units, AU, the planet is subjected to levels of ultraviolet and X-ray radiation far greater than anything experienced in our solar system. These high-energy photons are capable of breaking apart molecular bonds in the planet's atmosphere, leading to atmospheric escape, a phenomenon where lighter elements, such as hydrogen and helium, are stripped away into space. Observations have shown that WASP-121b is losing its atmosphere at an alarming rate, with gases forming a comet-like tail as they are blown away by the star's radiation. This intense radiation not only affects the atmosphere but also poses severe risks to any potential explorers. The lack of a magnetic field to deflect charged particles means that radiation would penetrate the planet's surface or any orbiting spacecraft, causing damage to both equipment and biological systems. Current radiation shielding technologies would be insufficient to protect against such high levels of exposure, requiring the development of advanced materials and energy-dissipating systems to ensure safety. The psychological effects of extreme environmental conditions on WASP-121b would also present significant challenges for human exploration. The planet's constantly deforming shape, combined with its volatile atmosphere and blindingly bright day side, would create an environment that is both disorienting and overwhelming. The lack of stable ground, combined with the ever-present threat of molten metal rain and radiation, would exacerbate feelings of isolation and fear. Prolonged exposure to such conditions could lead to psychological issues such as sensory overload, anxiety, and even space adaptation syndrome, a condition that affects astronauts in microgravity environments but could be amplified under such extreme circumstances. Addressing these psychological challenges would require innovations in habitat design and mission planning. Enclosed habitats with simulated Earth-like conditions, including artificial lighting and temperature regulation, would be essential to maintain mental and physical health. Furthermore, the use of autonomous robotics and remote exploration tools could minimize human exposure to the planet's hazards, allowing data collection and analysis to occur from safer distances. Despite its hostile nature, WASP-121b offers an extraordinary opportunity for scientific exploration. Its proximity to its host star and its extreme atmospheric conditions make it a natural laboratory for studying the physics and chemistry of hot Jupiters. By examining the processes that drive atmospheric escape, the effects of tidal forces, and the behavior of vaporized metals, scientists can gain valuable insights into the evolution of exoplanets in high-energy environments. These findings also have implications for understanding the diversity of planetary systems in the galaxy, as well as the factors that contribute to planetary habitability and longevity. The study of WASP 121b also challenges our understanding of planetary boundaries, expanding the range of conditions under which planets can exist. While the planet itself is uninhabitable, its unique environment provides a stark contrast to Earth, highlighting the delicate balance that makes our planet a haven for life. As researchers continue to push the boundaries of exoplanetary science, WASP 121b serves as a reminder of the vast and varied nature of the cosmos, where even the most extreme conditions can offer valuable lessons. The tidal forces exerted by the gravitational pull of the host star also play a significant role in shaping the planet's environment. The planet's close orbit, just 0.025 astronomical units from its star, results in intense gravitational interactions that not only deform the planet's shape but also contribute to tidal heating, a process where the planet's interior is heated by friction caused by the constant stretching and compressing of its surface. This heating drives additional geological activity, contributing to the planet's extreme conditions and making it an even more challenging place to explore. The orbital resonance between WASP 121b and its star further amplifies the tidal forces, leading to the planet's eccentric orbit and making it an even more fascinating object for planetary scientists to study. Radiation is another critical aspect of WASP 121b's hostile environment. Being so close to its parent star, the planet is subjected to intense ultraviolet and X-ray radiation. The radiation levels on WASP 121b are far greater than those on Earth and far beyond what human explorers could withstand without significant protective measures. The high levels of radiation can erode any atmosphere over time, preventing the planet from retaining volatile compounds, such as water. Additionally, the extreme radiation exposure poses significant risks to electronics, which would need to be heavily shielded to operate in such an environment. For robotic missions, advanced radiation-resistant technology would be required to ensure the longevity and functionality of any spacecraft sent to study the planet. One of the most significant challenges posed by WASP 121b is its psychological impact. The extreme conditions of the planet, the intense heat, constant radiation, molten metals, and tidal forces, make it a place where human life would be impossible. Even the thought of human exploration raises questions about the psychological toll that prolonged exposure to such an environment would have on astronauts. Isolation, exposure to constant danger, and extreme sensory inputs, such as blinding light or constant radiation, could lead to stress, anxiety, and even disorientation. If humans were ever to visit a planet like WASP 121b, these factors would need to be considered carefully in the design of habitats and life support systems. The study of these psychological challenges, even in the context of unmanned missions, is essential for understanding how future space explorers might cope with similarly extreme conditions in other parts of the universe. Despite the extreme conditions, WASP 121b remains an invaluable subject for scientific inquiry. Studying such a hostile and extreme world offers significant opportunities to push the boundaries of both planetary science and engineering. For example, WASP 121b's molten metal atmosphere challenges current models of planetary weather systems and atmospheric chemistry. Understanding how metals behave at high temperatures, how they interact with gases, and how these reactions shape the overall climate, and weather patterns could provide key insights into the workings of other gas giants, both within our solar system and beyond. Furthermore, the study of tidal forces, atmospheric radiation, and planetary geology on WASP-121b could inform models of planetary evolution, particularly in high-energy environments where the potential for habitability is low. The technological innovations required to explore planets like WASP-121b have far-reaching implications. To study this planet, advanced spacecraft shielding, autonomous robotics, and radiation-resistant electronics would be necessary. These innovations not only push the limits of what is possible in planetary exploration, but also have the potential to revolutionize other industries here on Earth. For example, materials designed to withstand extreme temperatures and radiation on WASP-121b could have applications in industries such as nuclear energy, space travel, and even medical technology, where radiation resistance is crucial for equipment and materials used in medical imaging or cancer treatment. While it is unlikely that humans will ever set foot on WASP-121b, the insights gained from studying this extreme planet will continue to inspire curiosity and innovation. The conditions on WASP-121b remind us that the universe is not static or predictable. Planets exist in every stage of their evolution, from potentially habitable worlds to places where life is impossible. In our pursuit of knowledge, planets like WASP-121b are essential in helping us understand how planets form, evolve, and survive in high-energy environments. These worlds expand our understanding of what is possible in the universe and challenge our assumptions about the conditions necessary for life to thrive. WASP-121b embodies the vast and varied possibilities of the universe, showcasing the incredible extremes that exist on exoplanets. Its environment, with molten metals in its atmosphere, extreme radiation, and intense heat, represents the outer limits of what we understand about planetary systems. These extreme conditions present a remarkable challenge for scientists, forcing them to rethink existing theories and develop new technologies capable of withstanding such harsh environments. The technological innovations driven by the study of planets like WASP-121b, such as radiation-resistant materials, advanced robotics, and thermal shielding, will play a key role in future space missions, enabling us to explore even more distant and challenging worlds. In addition to the technological advancements, the exploration of WASP-121b expands our knowledge of how planetary systems evolve and function, especially under conditions that are vastly different from Earth's. By understanding the atmospheric dynamics, geological activity, and other physical processes on such extreme planets, we can refine our models of planetary development. These findings also provide valuable context for the search for life, helping scientists recognize the limits and potential for habitability on other planets, even in systems far beyond our own. As we continue to study WASP-121b and other similar exoplanets, we gain deeper insights not only into the nature of distant worlds but also into the origin and evolution of our own planet. The knowledge we gain through this research strengthens our understanding of Earth's place in the cosmos, revealing both the fragility and resilience of our planet. Furthermore, the pursuit of exploring such extreme environments challenges humanity's imagination and determination, pushing the boundaries of space exploration. It raises important questions about what we can achieve as we look to explore new frontiers in the universe, testing the limits of human exploration and our understanding of the vast and mysterious cosmos. Cancri e, a scorching and volatile exoplanet, resides approximately 41 light-years away in the constellation Cancer. Orbiting its host star, 55 Cancri A, in just 18 hours, this super-Earth is a prime example of an extreme planetary environment. Discovered in 2004 via the radial velocity method, 55 Cancri E was one of the first super-Earths identified, making it a pivotal discovery in the study of exoplanets. Despite its rocky composition and classification as a super-Earth, its conditions are far removed from anything familiar to life on Earth. From its lava-filled surface to its seismically unstable environment, 55 Cancri E presents a world that is as mesmerizing as it is hostile. One of the most defining features of 55 Cancri E is its intense volcanic activity and lava-covered surface. The planet's proximity to its star, at a distance of just 0.016 AU, subjects it to extreme stellar radiation, heating its day side to temperatures exceeding 2,400 degrees Celsius, 4,350 degrees Fahrenheit. At such temperatures, rocks and metals melt, forming vast oceans of molten lava. Observations using the Spitzer Space Telescope suggest that the surface of 55 Cancri E is not uniformly molten, but instead features large, active volcanic regions interspersed with solidified terrain. These regions are thought to be constantly reshaped by volcanic eruptions, which release molten material and gases into the atmosphere. The volcanic activity on 55 Cancri E is likely driven by the planet's internal heat, which may be amplified by tidal forces exerted by its host star and neighboring planets. These forces stretch and compress the planet's interior, generating heat and fueling ongoing geological activity. The resulting lava flows, coupled with the planet's searing temperatures, create an environment that is as dynamic as it is unforgiving. For any hypothetical exploration mission, the constant reshaping of the surface would pose significant risks, as landing zones could be rendered unsafe within moments due to eruptions or lava flows. Adding to its hostility, the atmosphere of 55 Cancri E contains exotic gases that present unique challenges for exploration and survival. While the exact composition of the atmosphere remains a topic of scientific investigation, initial observations suggest the presence of gases such as carbon dioxide, methane, and potentially hydrogen cyanide, all of which are toxic to humans. The combination of these gases, along with the intense heat and pressure, creates a caustic environment that would corrode most materials and render traditional filtration systems ineffective. Advanced filtration technologies capable of removing toxic particles and adapting to rapidly changing atmospheric conditions would be essential for any exploration effort. The atmosphere also plays a role in shaping the planet's extreme weather patterns. High temperatures on the day side may lead to the formation of thick, reflective clouds composed of vaporized rock and metallic particles. On the night side, the seismic activity on 55 Cancri E further contributes to its instability. The constant tidal forces and internal heating not only fuel volcanic eruptions but also create conditions for frequent earthquakes and surface fractures. These seismic events could displace lava flows, disrupt solidified terrain, and release large amounts of gas into the atmosphere, altering its composition. For robotic or human exploration, this seismic activity poses significant challenges, requiring landing craft and habitats to be designed with enhanced structural stability and adaptability. Seismic monitoring systems would be critical for predicting and responding to these events, minimizing the risks to equipment and personnel. The psychological impact of exploring a planet like 55 Cancri E would also be immense. The alien landscapes, dominated by vast seas of molten lava and shrouded in toxic gases, would create a sense of isolation and unease for explorers. The constantly changing surface and violent eruptions would reinforce the perception of an unpredictable and hostile environment. Additionally, the concept of time dilation, caused by the planet's rapid orbit around its star, could have a disorienting effect on human perception. While relativistic time dilation is negligible in this case, the extremely short orbital period might create a psychological disconnection from the natural cycles of time experienced on Earth. For explorers, the knowledge that a year on 55 Cancri E passes in less than a single Earth day could exacerbate feelings of temporal alienation, making it harder to maintain a sense of normalcy. To mitigate these psychological challenges, missions to 55 Cancri E would need to incorporate advanced mental health support systems. Simulated Earth-like environments within habitats, including artificial lighting and temperature regulation, could help maintain circadian rhythms and reduce the stress of constant exposure to the planet's harsh conditions. Regular communication with Earth and immersive virtual reality systems could also provide a sense of connection and familiarity, alleviating the psychological burden of exploring such an alien world. Despite its extreme hostility, 55 Cancri E offers an invaluable opportunity for scientific research. Its dynamic geological activity provides insights into the processes that shape rocky planets under extreme heat and pressure. By studying the planet's volcanic activity, scientists can gain a better understanding of how internal heating and tidal forces influence planetary geology. The exotic atmospheric gases, while toxic to humans, offer a unique laboratory for studying chemical reactions in high-temperature environments, which could inform our understanding of atmospheric evolution on other exoplanets and even early Earth. The challenges posed by 55 Cancri E also drive technological innovation. Developing materials capable of withstanding intense heat, pressure, and corrosion is critical for future exploration missions, not only to this planet but also to similar environments elsewhere in the galaxy. These advancements could have applications beyond space exploration, such as improving materials used in high-temperature industrial processes on Earth. 55 Cancri E is a planet of extremes, defined by its lava-filled surface, toxic atmosphere, seismic instability, and the psychological challenges it presents to potential explorers. Its violent and unpredictable environment offers both challenges and opportunities, pushing the boundaries of our understanding of planetary science and engineering. While it is unlikely that humans will ever set foot on this volatile world, the study of 55 Cancri E continues to inspire innovation and deepen our appreciation for the diversity and complexity of the universe. It serves as a stark reminder of the vast and varied nature of exoplanets, where even the most inhospitable worlds have valuable stories to tell about the processes that shape the cosmos. Among the countless exoplanets discovered in recent years, LHS 3844b stands out as a stark and lifeless world that challenges the very notion of habitability. Located approximately 48.6 light-years away in the constellation Indus, LHS 3844b orbits its host star, a small M dwarf, in just 11 hours. Discovered in 2019 using data from NASA's TESS, Transiting Exoplanet Survey satellite, LHS 3844b is a rocky planet slightly larger than Earth, with a radius about 1.3 times that of Earth. While its proximity and rocky composition make it an intriguing subject for scientific study, its harsh conditions render it one of the most hostile environments yet observed. One of the defining characteristics of LHS 3844b is its lack of an atmosphere, a condition confirmed through detailed infrared observations conducted by NASA's Spitzer Space Telescope. The absence of an atmosphere leaves the planet completely exposed to cosmic radiation, including harmful ultraviolet, UV, and X-ray radiation emitted by its host star. Unlike Earth, which is shielded by its atmosphere and magnetic field, LHS 3844b's barren surface has no protection against these relentless and damaging rays. The constant bombardment of cosmic radiation would be lethal to any form of life as we know it, while also posing significant challenges for potential exploration missions. Robotic landers and other exploratory equipment would require advanced radiation shielding to prevent damage to their systems, while human missions would need to rely on heavily fortified habitats or subsurface shelters to ensure safety. The lack of an atmosphere also leads to severe temperature fluctuations between the planet's day and night sides. With no atmospheric layer to redistribute heat, the side of LHS 3844b facing its star experiences scorching temperatures of up to 770 degrees Celsius, 1420 degrees Fahrenheit, hot enough to melt many metals. In stark contrast, the night side plunges into freezing cold, likely dropping to temperatures below -250 degrees Celsius, -418 degrees Fahrenheit. These extreme temperature variations present a unique set of challenges for exploration. Any spacecraft or rover deployed to the planet would need to endure rapid and dramatic thermal shifts, requiring materials and systems capable of withstanding both extreme heat and cold without degrading or malfunctioning. The challenges for spacecraft landing and surface navigation on LHS 3844b are further compounded by its rugged, barren terrain. With no atmosphere to slow descent, landers would rely solely on propulsion systems to achieve a controlled landing. This approach increases the complexity and cost of missions, as the absence of aerodynamic drag eliminates the possibility of using parachutes or similar technologies. The planet's surface, likely littered with impact craters, sharp rocks, and fine dust, adds another layer of difficulty, as landers and rovers must be equipped to traverse unstable and abrasive terrains. Navigation systems would need to rely on advanced imaging technologies, such as LiDAR and infrared cameras, to map the surface and identify safe pathways for exploration. The absence of an atmosphere on planets like LHS 3844b actually has a dual impact on communication systems. On one hand, the lack of atmospheric interference allows radio signals to travel unimpeded, which is beneficial for long-range communication between the planet and Earth. This means that radio transmissions wouldn't face the typical challenges that occur in Earth's atmosphere, such as signal degradation. However, the intense radiation environment of such planets poses a major challenge. High levels of radiation can disrupt electronic systems, potentially corrupting or degrading the quality of data transmission. To mitigate this, any communication system would require robust shielding to protect the equipment from radiation damage. Additionally, error correction protocols would need to be in place to ensure that the data received on Earth is accurate and reliable, despite the potential for interference caused by the planet's harsh radiation environment. This complexity highlights the need for advanced technology to maintain communication over vast distances in space. Given the extreme conditions on LHS 3844b, the survival of human explorers would depend entirely on the development of advanced life support systems. These systems would need to provide oxygen, regulate temperature, and protect against cosmic radiation, all while operating in a resource-scarce environment. Habitats designed for LHS 3844b would likely be subsurface or heavily shielded structures to minimize exposure to radiation and temperature fluctuations. Energy generation would pose another challenge, as solar panels would need to endure the planet's intense heat and radiation on the day side while remaining functional in the freezing conditions of the night side. Alternatives, such as nuclear power or advanced battery systems, could offer more reliable solutions for sustaining life and powering equipment. The psychological challenges of surviving on LHS 3844b would also be significant. The planet's barren and desolate landscape, combined with its harsh conditions, would create an environment of extreme isolation. Without the familiar markers of life, such as vegetation or a dynamic atmosphere, explorers might struggle with feelings of alienation and sensory deprivation. To mitigate these effects, habitats could incorporate Earth-like features, such as artificial lighting that mimics sunlight, temperature-controlled environments, and virtual reality systems to simulate more hospitable surroundings. Despite its hostility, LHS 3844b provides a unique opportunity for scientific exploration. Its lack of an atmosphere allows researchers to directly study the composition and structure of its rocky surface, which could provide clues about the planet's formation and geological history. The extreme conditions on LHS 3844b also make it an excellent analog for understanding rocky planets in similar environments, particularly those orbiting M-dwarf stars, which are the most common type of star in the Milky Way. By studying LHS 3844b, scientists can gain insights into the processes that shape rocky planets under high-energy radiation and tidal forces, as well as the factors that contribute to atmospheric loss. The study of LHS 3844b plays a crucial role in refining our search for habitable exoplanets. While the planet itself is inhospitable, its extreme characteristics, such as its lack of atmosphere, offer a sharp contrast to more temperate worlds. By understanding how planets like LHS 3844b evolve without an atmosphere, scientists can better identify what makes planets capable of supporting life. This information helps to redefine the conditions necessary for habitability, allowing for a more accurate assessment of which exoplanets may have the potential to support life. Furthermore, studying planets like LHS 3844b aids in the development of planetary models that enhance our understanding of how rocky planets form and develop in challenging environments. This research is crucial for determining the true limits of habitability across the galaxy, expanding our search for life on other worlds. LHS 3844b is a world defined by its lack of atmosphere, extreme temperature fluctuations, and hostile terrain, making it one of the most uninhabitable exoplanets discovered to date. Its challenges, from radiation exposure to surface navigation, highlight the need for advanced technologies and innovative strategies for exploration. At the same time, its unique characteristics provide invaluable insights into the nature of rocky planets and the diversity of planetary systems in our galaxy. While it is unlikely that humans will ever set foot on LHS 3844b, the study of this extreme world continues to expand our understanding of the universe and the resilience required to explore its most hostile corners. HAT P7b, located approximately 1,040 light-years away in the constellation Cygnus, is a planet that epitomizes the extremes of alien worlds. Discovered in 2008 using the transit method, HAT P7b is a hot Jupiter, a gas giant with a mass about 1.8 times that of Jupiter and a radius nearly 40% larger. Its close proximity to its host star, a Type F star hotter and more massive than the Sun, subjects HAT P7b to conditions that make it one of the most hostile planets ever discovered. With scorching temperatures, violent storms, and surreal weather phenomena like molten sapphire and ruby clouds, HAT P7b is an extraordinary example of the harsh environments that exist in the universe. The most defining feature of HAT P7b is its scorching temperatures on the day side, which can exceed 2,500 degrees Celsius, 4,500 degrees Fahrenheit. This extreme heat is due to the planet's close orbit, at a distance of just 0.04 astronomical units, or about 6% of the Earth-Sun distance, completing an orbit in just 2.2 Earth days. At these temperatures, even metals like iron and aluminium vaporize, creating a searingly hot atmosphere dominated by exotic chemical processes. The planet's day side glows faintly due to thermal radiation, while its night side, though cooler, is still inhospitable, with temperatures hovering around 1,000 degrees Celsius, 1,800 degrees Fahrenheit. Adding to HAT P7b's hostility are its hurricane-scale storms, driven by its tidally locked nature, where one side of the planet permanently faces the star while the other side remains in perpetual darkness. The stark temperature contrast between the day and night sides creates violent atmospheric dynamics, including supersonic winds that can exceed speeds of 5,000 miles per hour, 8,000 kilometers per hour. These winds transport heat and vaporized materials from the day side to the night side, fueling massive storms that dominate the planet's atmosphere. Observations using the Kepler Space Telescope have revealed fluctuations in the planet's brightness, attributed to these dynamic weather patterns, including storms large enough to span the entire planet. One of the most surreal aspects of HAT P7b's atmosphere is the presence of molten sapphire and ruby clouds, a phenomenon resulting from the planet's unique chemical composition. The intense heat on the day side vaporizes minerals such as corundum, the crystalline form of aluminium oxide, which condenses on the cooler night side to form clouds of molten sapphires and rubies. These clouds, driven by the planet's fierce winds, create a striking visual contrast between the glowing day side and the shimmering, reflective clouds on the night side. While beautiful in concept, these clouds are deadly in practice, as they consist of materials that are not only abrasive but also capable of corroding spacecraft and equipment. The duality of HAT P7b's atmosphere, between the blazing day side and the stormy, mineral-laden night side, poses significant challenges for exploration. The tidally locked nature of the planet creates an environment that is both physically and logistically difficult to navigate. On the day side, the intense heat would destroy most known materials, requiring the development of advanced heat-resistant alloys and thermal shielding for spacecraft. On the night side, the abrasive sapphire and ruby clouds, combined with high-speed winds, would create mechanical challenges for landers and probes. The constant turbulence and lack of atmospheric stability would make it nearly impossible to establish a stationary presence or conduct long-term exploration. Human exploration of HAT P7b would be unfeasible with current technology. The lack of a solid surface, combined with the extreme heat, radiation, and dynamic weather, would prevent the construction of habitats or other infrastructure. Any missions to the planet would need to rely entirely on robotic explorers, designed to withstand the hostile conditions and equipped with advanced sensors to collect data remotely. These robotic systems would also need to operate autonomously, as the distance from Earth would result in significant communication delays, making real-time control impractical. Despite these challenges, studying HAT P7b offers valuable lessons for future missions to extreme planetary environments. The violent storms and unique atmospheric composition provide a natural laboratory for understanding the dynamics of gas giants and the behavior of weather systems under extreme conditions. By examining the mechanisms that drive heat redistribution and storm formation, scientists can refine their models of atmospheric physics, which can be applied to both exoplanets and gas giants within our solar system, such as Jupiter and Saturn. The study of HAT P7b also highlights the importance of preparing for tidally locked planets in the search for habitable worlds. Tidally locked exoplanets are common, particularly around M-dwarf stars, which constitute the majority of stars in the galaxy. Understanding how these planets maintain heat distribution and atmospheric circulation is crucial for assessing their potential habitability. While HAT P7b is far from habitable, its atmospheric dynamics provide insights into how tidally locked planets might sustain more temperate conditions in their terminator zones, the boundary between the day and night sides. Technological advancements inspired by the study of HAT P7b could have far-reaching applications. For instance, the development of heat-resistant materials capable of withstanding extreme temperatures and corrosive environments could benefit industries on Earth, such as aerospace engineering and high-temperature manufacturing. Similarly, innovations in autonomous robotics and remote sensing technologies could enhance our ability to explore other harsh environments, both on Earth and in space. In addition to its scientific contributions, HAT P7b serves as a reminder of the diversity and complexity of exoplanets in the galaxy. Its alien beauty, with molten sapphire clouds and glowing thermal radiation, contrasts sharply with the serene landscapes of Earth, emphasizing the vast range of conditions under which planets can exist. By studying these extremes, scientists can better understand the processes that shape planetary systems and refine their search for worlds that might support life. HAT P7b is an extreme exoplanet, defined by its scorching temperatures, hurricane-scale storms, and surreal weather phenomena, making it one of the most hostile planets discovered. With a surface temperature that can reach up to 2,500 degrees Celsius, 4,532 degrees Fahrenheit, it is far too hot for life as we know it. The planet experiences violent storms, driven by the stark temperature contrast between its day and night sides, where winds can reach several thousand miles per hour. These conditions push the limits of our understanding of planetary atmospheres, forcing scientists to reconsider what makes a planet habitable, and how extreme environments can form. Though human exploration of HAT P7b is not feasible due to its extreme conditions, the planet offers valuable lessons for scientific and technological progress. Studying HAT P7b's atmosphere, storms, and weather patterns contributes to our understanding of atmospheric physics and the dynamics of gas giants in high-energy environments. The technological challenges in studying such a planet, such as developing instruments to withstand extreme heat and pressure, also drive innovation in space exploration technology. HAT P7b's extreme nature highlights the vast diversity of planets that exist beyond our solar system, and underscores the ingenuity required to explore and understand the farthest reaches of the universe. Its study helps us push the boundaries of what is possible in planetary science, inspiring future exploration, and deepening our knowledge of the cosmos. We'd love to hear your thoughts in the comments below. If you found this exploration of space bodies fascinating, don't forget to like, share, and subscribe for more thrilling insights into the wonders of the universe. Thank you for journeying with us here on Frontiers of Infinity.